Okay, so welcome back to this next video in which we are discussing cyclic groups and cyclic subgroups. Okay, right. So we now discussed the finite cyclic groups. Okay, what we're now going to turn our attention onto is looking at the infinite cyclic group. Now, we have actually seen the infinite cyclic group in previous videos in this playlist on group theory, although we didn't actually call it ever that. Okay, the infinite cyclic group is in fact actually the group of integers under addition. Okay, so what I want to do is show you how the group of integers under addition can be thought of as a generalization of these finite cyclic groups to the infinite case. Okay, so let's think about how we would go about generalizing what we have done with finite cyclic groups to the case of infinite cyclic groups. Okay, well, when we were looking at finite cyclic groups, we were looking at the cyclic set permutations of the set containing 1, 2, 3, all the way up to little n elements. So all the natural numbers up to and including little n. So a natural thing to think would be maybe to generalize the concept of a finite cyclic group. All we're going to do is consider the set of the entire natural numbers, okay, and look at cyclic set permutations of the set of the entire natural numbers. Well, let me show you that there is a problem with that. Okay, so if you try and do that, okay, if you think about cyclic set permutations of the set of all natural numbers, so now we're looking at this infinite set of natural numbers here, okay, then it starts off absolutely fine. We can think of the identity set permutation easily. 1 will go to 1, 2 will go to 2, 3 will go to 3, 4 will go to 4, 5 will go to 5, and so on. So the identity cyclic set permutation works brilliantly if we're thinking of this set of the entire natural numbers. Okay, however, you get problems when you now try to do anything other than that. Okay, so now let's consider the cyclic set permutation where we're going to move everything to the right by 1. Okay, so let's have a look at this. So once again, I'll draw my set out. So 1, 2, 3, and it will go on. Okay, and here's the set again. 1, 2, 3, and it will go on. So 1 now will go to 2 because we're moving everything to the right by 1. 2 will go to 3, 3 will go to 4, and you can go on and on and on. Okay, but there is a problem here. Which element is going to be mapped onto 1? Okay, well, your answer will probably be the biggest element, but there is no biggest element. Okay, so can you name me an element of the natural numbers that will actually be mapped onto 1? And the answer is no. Okay, so then we have to ask the question, is this a set permutation? And the answer is no, because it's not bijective. Specifically, it's not surjective. Okay, it's not an onto map. Okay, so we fail. Okay, so if we think of trying to look at the cyclic set permutations of the actual natural numbers, we hit this horrible problem, basically, that what we would like to be a cyclic set permutation isn't actually even a set permutation. Okay, so we need a new idea. Okay, so what we're going to do is we're going to go to a bigger set. So we're going to throw away this idea of looking at the cyclic set permutations of the natural numbers, and we're going to look at the cyclic set permutations of a bigger set, basically. Okay, and the bigger set that we're going to look at is the set of all integers, basically. Okay, so the integers is bigger than the set of natural numbers. The integers, for a start, contains 0, okay, and in addition it contains all the negative whole numbers, not just the positive whole numbers. So it will contain 1, negative 1, 2, negative 2, 3, and negative 3. Okay, so we are now going to consider then the cyclic set permutations of this set of integers, basically. Okay, right, and let's try and understand why this solves this horrendous problem that we have here of nothing ever being mapped onto 1. Okay, so let's go over the page and have a look at the cyclic set permutations of the integers. Okay, so the way I'll draw the integers is I'll have 0 at the centre, I'll have 1 here, I'll have negative 1 here, 2 here and negative 2 here, and of course it will go on in both directions basically, and that really is the key to this. That's why this is actually going to work, okay, because we don't just have it going infinitely off in one direction, we also have it infinitely going off in the other direction as well. Okay, right. So, then I'll put the set again. So here is negative 2, negative 1, 0, 1, 2. So once again, we can define the identity set permutation. That will work absolutely fine. Every element will just be carried onto itself. And I suppose I should do it just for the sake of completion. So I'll write out the identity element here, where we move everything along by nothing. Okay, but now let's have a look at something more interesting. So let's now have a look at the cyclic set permutation, where we actually move everything along to the right by a certain amount, basically. And we'll start off by just moving everything along to the right by 1. So 0 will go to 1, 1 will go to 2, 2 will go to 3, negative 1 will go to 0 here, negative 2 will go to negative 1, negative 3 will go to negative 2. And basically this will be a set permutation. It is a bijective map, okay, it is injective, it's certainly one-to-one, and every element in our codomain here will have some other elements in the domain being mapped onto it. Okay, if you give me any little z, which is an element of the integers, I can find you another integer that is being mapped onto it. Just take the integer z minus 1 basically, and that one will be mapped onto z basically when you do this mapping of moving everything to the right by 1. Okay, right, so this gets around that problem basically, and it's all because we now have it an infinite number of negative integers over here basically, which we didn't have in the case of natural numbers. The natural numbers, the problem with it was that it was infinite in one direction, but then it would have a blunt end, a finite end on the other side. Okay, and that was a big problem because that meant that the element 1 didn't have anything being mapped onto it when we looked at this mapping where we moved everything 1 to the right by a certain amount. Okay, whereas now we've got around that problem. Okay, right, so there is the cyclic set permutation where we move everything along to the right by 1. You could go on, you could then have the cyclic set permutation where you move everything along to the right by 2, the cyclic set permutation where you move everything along to the right by 3, the cyclic set permutation where you move everything along to the right by 4. Okay, so you could create a lot of cyclic set permutations where you're moving things along to the right by a certain amount. Now, that's just like what we saw in the case of finite cyclic groups. However, there is a big difference here. Okay, in the case of finite cyclic groups, we could think of movements to the right as being equivalent to movements to the left. Okay, you could rethink of all of those finite cyclic permutations as cyclic permutations where we're moving things to the left rather than moving things to the right. And the reason for that was because of the way that we were cycling things back round again when we run out of things on this side to move things up to. Okay? Whereas in this case, where we're dealing with this entire set of integers, we do not have any of that cycling, okay, because we will never run out of something to move it onto, basically. Okay, so you cannot now think of a movement to the right as also being a movement to the left. Okay, so that means that if we're going to create a group of cyclic set permutations of this set of integers, we also need to put in all of the movements to the left. They are different cyclic set permutations to the movements to the right in this case. So let me now put in the cyclic set permutation where we move everything along to the left by 1. Okay, so here once again is our set. Okay, like so. And now what we're going to do is move everything along to the left by 1. So 0 will go to negative 1, negative 1 will go to 2, 1 will go to 0, 2 will go to 1, 3 will go to 2, and negative 2 will go to negative 3. Okay, so we are going to need to put in all of these movements to the left as well, basically. We're going to need to have a symbol representing them in our infinite cyclic group as well. Okay, so now that we've considered this set of integers, we've considered the cyclic set permutations of this set of integers, now what we need to do is actually create this infinite group. Okay, so the way that we're going to do this is we're going to give the cyclic set permutations of this set of integers symbols. We're going to put all of those symbols into a set, and then we're going to define the composition law on that set of symbols by thinking in terms of the composition of the set permutations that the symbols represent. Okay, right, now this is where it becomes confusing, because I am actually going to use the same symbols that I used for this set, okay, which we were thinking of the cyclic set permutations of, namely the set of integers. I'm going to use the same symbols from this set to represent the cyclic set permutations of this set, as I used for the actual set, basically, okay? Do not let that confuse you, okay? I'm just using symbols again, basically. I'm just being efficient, okay? There's nothing to stop me doing that. I'm just using symbols again, but I'm using them in a different context, okay? So just don't let that confuse you. So what I'm going to call this cyclic set permutation, which moves everything along by nothing, the identity permutation here, I'm going to call that 0. Okay, I'll put some colour on here. Okay, so here this cyclic set permutation is now going to be represented by the symbol 0. Okay, this cyclic set permutation, where I move everything along to the right by 1, that is going to be represented by the symbol +1. Okay, so positive 1. Okay, then all of the other movements along to the right, they will be represented by the symbol which tells you how much you've moved along to the right. So for instance, the cyclic set permutation where you move everything 2 to the right, and I'll just do this as an example. Okay, so here is the set once again. Okay, and now what we're going to have is the movement 2 to the right. So 0 will go on to 2, 1 will go on to 3, 2 will go on to 4, negative 1 will go on to 1, negative 2 will go on to 0, negative 3 will go on to negative 1, and negative 4 will go on to negative 2. We will represent this as +2 basically, and you can go on, okay? Movement to the right by 3 will be represented by 3. Movement to the right by 4 will be represented by 4, okay? So movements to the right are going to be represented by the positive numbers, so what do you think we're going to represent movements to the left by? Okay, well quite simply we're going to represent them by the negative numbers. So movement 1 to the left, like so, is going to be represented by -1. Okay, then movement to the left by 2 will be represented by -2, movements to the left by 3 will be represented by -3, etc. on and on. Okay, so now what we do is we put all of these symbols into a set, which is of course the set of all integers, so we'll have 0, 1, -1, 2, -2, and this set now is going to form our group, and this is why it gets confusing. Our group is the same set of symbols as the set that we were thinking of set permutations of. Okay, but don't let that confuse you. We are thinking of these symbols now as not just being symbols, but as representing these set permutations. So these have a lot more meaning attached to them than the symbols did here. Here they were just silly symbols that someone had made up. Okay, now they suddenly have a meaning in terms of set permutations attached to them. Okay, and to turn this then into a group, what we're going to do is we're going to have a composition law on this. Okay, and the normal way that we call the normal thing that we call this composition is addition, basically. Okay, so if I take an arbitrary little element, little x, and I compose it with an arbitrary element, little y, and I want the answer x composed with y, what that's going to mean is first do the cyclic set permutation y, and then do the cyclic set permutation x, basically, as it did in the case of the finite cyclic groups. Okay, so let's just think of an example to get some intuition here. Okay, so if we do, for instance, 2 plus 3, what is that now going to mean? That's going to mean firstly do the cyclic set permutation where you move everything along by 3 to the right. Okay, so you'll move everything along to the right by 3, then do the cyclic set permutation where you move everything along to the right by 2, okay, that means that overall, what are you going to do? You're going to move everything along to the right by 5. That's now the next cyclic set permutation. So the answer to this is, of course, 5, because 5 is the symbol that we use to represent the cyclic set permutation where you move everything along to the right by 5. Okay, so that's how you can think of this group of integers under addition as being this infinite cyclic group in this way. Okay, and let's just go through why this infinite cyclic group is actually going to be a group under this composition law. So let's just explain why it will be closed, why it will be associative, why it will have an identity, and why it will have inverses. Okay, so closure firstly. How am I assured that if I compose any two integers together under this composition law that I've created here, that I will end up with another element of my set of integers? Okay, so again, this amounts to understanding that when I compose two cyclic set permutations together, I end up with another cyclic set permutation. Okay, so if I want to add two integers together, what I need to do is think back to what cyclic set permutations they represent and compose those together. Okay, now if I compose one set permutation of the form move everything along by a certain amount with another set permutation of the form move everything along by a certain amount, what I end up with is still a set permutation of the form move everything along by a certain amount. You can't possibly end up with a set permutation that doesn't have that structure. This set, this group here, consists of a symbol representing every single cyclic set permutation of the set of integers. There are no more, okay? You can't come up with any other set permutation of the form move everything along by a certain amount that isn't covered within this set of symbols, basically. We have represented every single one in this group of integers, basically. Okay, so that means that when we compose any two integers together, the answer must be an integer, because when we compose any two cyclic set permutations together, it must give a cyclic set permutation, and we have got every single cyclic set permutation represented in our group of integers. So that's why it's closed. Okay, associative, we know we're thinking in terms of set permutations, and the composition is in terms of composition of set permutations, and therefore we instantly get associativity. Okay, so next up, the identity element. Okay, we need to prove that there is an element in here which will compose with any other element to give that other element back again. Again, that's just true because we have an element representing the identity map here. Okay, so when you think of adding 0 onto any other element, composing 0 with any other element, okay, you'll think of composing the identity map with the set permutation represented by that other symbol. Okay, and when you compose the identity set permutation with any other set permutation, it just gives that other set permutation back again, which is why 0 will add to any other integer to give the other integer back again. Okay, finally we need to make sure that it has inverses. Okay, so we need to make sure that for any symbol represented in our group here, we have another symbol that will compose with it to give the identity back again, and that's just because we have inverse cyclic set permutations, basically. Okay, so if you take any cyclic set permutation, I can find you an inverse map for that, which is also a cyclic set permutation. Okay, so for instance, moving to the right by a certain amount, there will be another cyclic set permutation of the form moving to the left by that same amount, and if I compose those two together, I will then get the identity map, i.e. moving along by 0 back again, basically. So for instance, if I have the cyclic set permutation where I move everything along to the right by 4, which will be represented by the symbol 4, then I'll also have the cyclic set permutation where I move everything along to the left by 4. That will be represented by negative 4, and 4 plus negative 4 must then be equal to the identity map. Okay, must equal 0, basically, because those two cyclic set permutations composed together have to give the identity cyclic set permutation back again. Okay, right. So that's why we have inverses, because for any cyclic set permutation, its inverse map is another cyclic set permutation and therefore is represented somewhere within this set of symbols, which means that for any symbol here, you can find another symbol in here which will compose with it to give the identity symbol back again. Okay, so that's why it forms a group. Okay, right. In fact, it's actually going to be an abelian group, as are the finite cyclic groups. Now, I didn't actually say that when we discussed finite cyclic groups, but they will be abelian groups as well. And quite simply, the reason it's an abelian group is that if you compose two elements, let's say x with y, okay, and both of these are representing cyclic set permutations, when you compose those two cyclic set permutations together, as we should do in order to work out what the two elements composed together is equal to, basically it doesn't matter what order you compose two cyclic set permutations together in. If you have an instruction which is move everything along by a certain amount, and then you do another instruction which is move everything along by another amount, then it doesn't matter if you do it in the opposite order, basically. The answer is still the same, okay, because, you know, when you move, to do an example, let's do an example to get some intuition for this. If we take the cyclic set permutation where we move everything along to the right by 4, and then we compose that with the cyclic set permutation where we move everything along to the left by 3, okay, it doesn't matter if we first move along by 4 and then move along to the left by 3, okay, to give moving along to the right by 1 overall, or if we do it the other way around, we first move along to the left by 3 and then move along to the right by 4, again it will give the same answer of moving along to the right by 1. So because of the way that you can think of the elements of these cyclic groups as representing these cyclic set permutations, and the composition law as representing the composition of those cyclic set permutations, it means that composition in these cyclic groups is abelian, is commutative. Okay, right, so the integers under addition, the group of integers under addition then, is the infinite cyclic group. Okay, it's the generalization of the finite cyclic groups that we've studied in previous videos. Okay, right, and together the finite cyclic groups with this infinite cyclic group, together they are called the cyclic groups. Okay, right, so that now concludes our discussion of cyclic groups. In the next video, what we'll turn our attention onto is the topic of cyclic subgroups.